Hello everyone, welcome to the lecture 50 in the course Diffusion in Solids. So today's lecture is a tutorial lecture, and we will be covering some problems on diffusion in intermetallics, in nano and quasi-crystalline materials, and in metallic alloys. So let's see the question number 1. Which of the following groups contain isostructural intermetallics? What we mean by isostructural is that those having the similar crystal structure. See, the intention of this question is not really to test your memory, but to actually impress upon you the fact that you should not think that if the formula of an intermetallic or two intermetallics are same, then they will be isostructural. That need not be the case. It depends upon actually the elements which are involved. So, for example, in this question, if you see Ni3Al, Ni3Ga, Ni3Ge, all have the same structure as it is also given in this table. This structure is L12 structure. Whereas, if you see the Ni3Al, Cu3Sn and Ni3Sp. So, Cu3Sn and Ni3Sp actually have a DO3 structure. So, this is not same as Ni3Al, which is L12. So, even if the stoichiometry, the chemical formula is still A3B, the structure of these intermetallics are different. So, similarly, if you see NiAl, COAl and CuZn, all three are having a B2 structure. But if you compare copper and gold, CuAu, COPT, AuZn, they are not isostructural, because COPT you can see has a L10 structure. So, this I hope you will remember that if you see two intermetallics having the same chemical formula, they need not be isostructural. Okay, it depends upon the actually the elements which are involved. Now, second question is the copper zinc undergoes an order disorder transition when heated beyond 741 Kelvin. Which of the following phenomena accompanies this transition? So, order disorder transition during heating, does it lead to increase in activation enthalpy of diffusion, decrease in activation enthalpy of diffusion, appearance of superlattice peak in X-ray diffraction pattern, or disappearance of superlattice peaks in the X-ray diffraction pattern? So, this we saw that when you go from order to disorder, there is a change in the diffusivities, the diffusivity increase, or in other words, it is accompanied by a decrease in activation enthalpy of diffusion. Secondly, the ordered structure is characterized by what are known as superlattice peaks in the X-ray diffraction pattern. So, these are the peaks which will normally not be visible for, let us say, a BCC structure, but for an ordered B2 structure it will be visible in the XRD pattern. They are low intense peaks. So, when alloy goes from ordered to disordered structure, then the superlattice peaks will disappear. So, just to show you, so this is the part that we saw, that when it becomes disordered, the enthalpy decreases, and this is the typical pattern of a B2 structure. So, these are the superlattice peaks. So, for example, 100 is not usually seen in a BCC structure, because you have the extinction rules where the sum should be even. But that changes for B2, and these are the superlattice peaks you see here marked by the arrows. When you heat it, then these superlattice peaks will vanish and you will have a conventional E2 structure, which is BCC. So, the correct option is B and D. Now, question number 3, identify the missing step in the following 6 jump cycle sequence which causes a net displacement in 110. So, we saw that in 110 first there is let us say if the vacancy is at A, then the first jump makes first exchange happens such that now the vacancy moves to the B side and a B atom moves to the A side, creating an anti-side defect. This is followed by a couple of sequences, and this, if you see this this particular atomic arrangement where you have vacancy on B side and 2 anti-site B atoms and 1 anti-site A atom. So, after this again the jumps happen to restore the order. So, this is very similar to what is given here. So, you can see the sequence also. So, VA, VB plus BA, then VA plus BA plus AB, then two anti-site B atoms are present, after which then the order restoration starts again, and you have VA plus BA plus AB. So, the correct option is in this case is B. So, a possible jump sequence which causes a net 100 displacement of vacancy via 6 jump cycle mechanism in B2 intermetallics is shown below. So, this is the cycle we saw during the lecture. This is the bent cycle. Can you think of another possible jump sequence which would result in same 100 net displacement? So, as I have always said, please before moving forward with the video, if you can try out on your own, your understanding will improve much further. So, the question is that can we identify another sequence of jumps which will cause a net 100 displacement? So, the answer is given here. So, in this what happens is the vacancy exchanges in the first jump, it exchanges a position with this B atom here. Now, you have in the second, this vacancy creates exchanges a position with this A atom such that an anti-site is created. Then the vacancy will move to this B atom, it exchanges position with this B atom such that now you will have two anti-site B atom, one anti-site A atom, and the vacancy is also on the B side. Then after that, the exchange happens with this B atom. So, this B is back to its own sublattice and vacancy is present on the A sublattice. In the fifth jump, again vacancy moves to this A atom, and A atom is restored back onto its lattice, and final step, vacancy exchanges position with this particular B atom here. So, afterwards what has happened, the net displacement has come in this particular direction. This, if you can observe, this is pretty much straight. So, this is also known as a straight cycle, whereas the previous sequence of jumps, it is referred to as bent cycle. Question number 5. Compound Al45 Ni55 shows a B2 structure. Which of the following is a generally observed as a dominant diffusion mechanism in this intermetallic? So, remember AlNi, we saw that AlNi at equiatomic, it is not a line compound. So, it is not just 50-50, but towards both left and right, the NiAl is stable, the compound is stable. And in this given composition, which is given in the question, it is a Ni rich composition. So, Ni rich composition, we have seen that the correct answer is the anti-structural bridge mechanism. The nickel rich side, this compound, the diffusion happens by ASB mechanism. So, this but we have to also remember that this happens after a percolation threshold is reached, that is the sufficient concentration of the anti-site atoms. So, this is again illustrated for your reference. So, here vacancy makes first jump with this A atom, it exchanges position with this A atom, then so that the anti-site atom is created, then vacancy exchanges its position with this anti-site atoms, and then such a configuration is observed. So, you need a certain anti-site concentration for this mechanism to be observed. Question number 6, in most of the binary intermetallics, diffusivities of the constituents are nearly same, true or false. This we have seen the various mechanisms also indicate that, for example, 6 jump cycle mechanism, triple defect mechanism, or we just now saw ASB mechanisms. Everywhere both A and B are involved, because why the jump sequences are long, so that the order is the long range order is maintained. So, to maintain the long range order, a sequence of jumps is involved, which involves both A and B, and therefore, you see that in most of the binary intermetallics, the diffusivity of constituents are not very different. and therefore this statement is true. Question number 7, a cube of unit edge length is cut into 64 small cubes and assume that these all small cubes have a similar dimensions. Estimate the increase in surface area to volume ratio. So, the correct answer is 4 times, that is the increase in the surface area to volume ratio. Let us see how we can derive it. So, let us say initially when you have a cube of unit edge length, then the volume is a cube, which is equal to 1, and the surface area, the total surface area is 6a square, which is equal to 6. So, the surface area to volume ratio A by V is nothing but 6. Now, when this cube is cut into 64 small cubes all identical, then V is equal to Vs, where Vs is total volume of all small cubes. Now, this if you say edge length of the initial cube was A and the volume of edge length of the small cubes, each of the small cube is As, then A cube is equal to 64 times As cube. So, you can see As is equal to 1 by 4, and we know that Vs, that is the total volume of all small cubes, is equal to 1. So, therefore, the total surface area As is equal to 64 into 6 into A square, which turns out to be 24. So, now the surface area to volume ratio is equal to 24, which is 4 times of the previous when there was only one cube of unit edge length. Let us move to question number 8. Derive the transition times for evolution of kinetic regimes in the following cases: C to B2 in coarse grain polycrystals, B2 to B2 dash in the fine grain polycrystals, and C to C dash in ultra fine grain polycrystals. So, we have seen first for the transition to occur from C to B2 in the coarse grain polycrystals, the length of diffusion in grain boundary in the C regime should be equal to length of diffusion in grain boundary in B regime. So, that is how C to B2 transition can happen, and if you equate that, then length of grain boundary in C regime is given by root dGB into T, whereas length of grain boundary diffusion in B regime is given by root SdGB delta divided by 4 d to the power 1 by 4 into t to the power 1 by 4. So, if you equate this then and equate and do some algebraic arrangements, then you end up in the transition time t being s square delta square by 4 d. So, this was denoted by t dash in the original lecture. This is the transition time. For B2 to B2 dash in the fine grained structure, we have this happening when the bulk diffusion length becomes equal to the grain boundary diffusion length in the B kinetic regime. So, the root dt is equal to the LGB in B regime, and when you equate that, then again do some simple rearrangements, and you will get the value of transition time t is equal to s dGB delta whole square divided by 4d cube. This was represented as t double dash. And C to C dash, this happens when the LGB of in C kinetic regime is equal to the grain size d. So, that says that root dGB t is equal to d, and therefore, t is equal to d square by dGB. Moving ahead, for the conditions dGB far greater than d and g very less than 1, the ratio of effective diffusivity is given by Hart equation to that given by Maxwell's equation is equal to. So, let us see the Hart, so the correct answer is 3 by 2. Let us see how we can arrive at that. So, the effective diffusivity given by Hart equation, which is for a coarse grain polycrystal, is equal to G into dGB plus 1 minus G into D. So, if G is very less than 1, then this becomes equal to 1, and therefore, the Hart effective diffusivity is G dGB plus D. Since dGB is much greater than D, we can write effective Hart diffusivity is equal to G into dGB. Now, Maxwell's equation, the D effective is given by this expression, dGb is equal to 3 minus 2G into D plus 2G into dGb divided by GD plus 3 minus G into dGb. So, if I take 2 common from here, I have 3 by 2 minus G into D plus G dGb in the denominator and in the numerator, and the denominator remains the same. Since G is very less than 1, so this term can simply be written as 3 dGb, and this particular term can be written as 3 by 2 D. So, now if I take 3 by 2 common and 3 common from the denominator, I get dGb plus GD by 3 and 2 by 3 GdGb plus D. Since again the D is much smaller than dGb, so this terms can be neglected, and what we end up in is the ratio so the D effective in Maxwell's case is 2 by 3 G dGb. So, if you take the ratio of both of them, it comes to be 3 by 2. Question number 10, quasi-crystals exhibit translational periodicity but do not show rotational symmetry, true or false? This is a false statement. Quasi-crystal shows a rotational symmetry. They have a 10-fold axis. For example, here they can have a 5-fold axis or a 12-fold axis. So, they do show a rotational symmetry, but they do not show the translational periodicity. What they show is known as the quasi-periodicity. We saw this when we were talking about the quasi-crystals, that quasi-periodicity is characterized by a golden mean of the Fibonacci series. So, this statement is false. They do not show periodicity, but they show rotational symmetry. Question number 11, radio tracer diffusion and SIMS are widely used for techniques for diffusion measurement. However, AL self-diffusion data for AL-rich quasi-crystalline phase or alloys has not been reported in literature through these methods. What is the appropriate reason? So, the first is half-life of AL isotope is very short. This is not correct. AL isotopes are very expensive. Natural AL is monoisotopic, or AL isotopes are hazardous. So, the correct reason is that the natural AL is monoisotopic. There are no isotopes available for aluminum, and that is why you cannot use a radioactive technique or SIMS kind of technique to understand aluminum self-diffusion. Question number 12, for which of the following quasi-crystalline alloys diffusion coefficient will contain 2 principal components? So, we have seen this before also, that diffusion coefficient is a scalar quantity if the structure is isotropic. If it goes to a uniaxial structure, if the crystal structure is uniaxial, then you need 2 components. If it becomes triclinic or something, then you need at least 3 principal components. So, these are the structures: icosahedral, decagonal and dodecagonal. So, if you see the first 2 alloys, they are in the icosahedral quasicrystals. So, icosahedral is a completely isotropic and a symmetric structure. Therefore, only 1 principal diffusion coefficient is sufficient. So, these are not the correct options, but the other 2, AL64 CO16 CU20 and AL17 Fe5 and I24, both belongs to decagonal structure, which has axis, and therefore 2 components are required, one perpendicular to the decagonal axis, another parallel to the decagonal axis. Next, select the correct statements about diffusion in icosahedral aluminum, palladium, manganese quasicrystalline alloys. So, the first option is diffusion of transition element solutes is faster than the non-transition element solutes. This is not correct because actually the transition element solutes diffuse slower than the non-transition element solutes. Diffusion is isotropic. This is correct because it is an icosahedral structure. So, diffusion is isotropic, or 1 single diffusion coefficient is enough to describe the complete behavior. Activation volume of transition element solutes is higher than the non-transition element solutes. This is not correct. We had discussed this, that even though the diffusion of transition elements solutes is much slower, the activation volume which marks the pressure dependence is same for transition element as well as the non-transition element solutes. So, this is not correct. diffusion is dominated by vacancy mechanism. This is again true. So, this is written by mistake here. The correct option should be B and D. So, maybe I will just cancel it. So, moving ahead, question number 14. Comparison of self-diffusivities of FCC and BCC metals reveals which of the following trends? So, the first is diffusivity at melting temperature is higher for FCC metals than BCC metals. This is not correct because FCC is a close packed structure and therefore, the diffusion at the melting point is slower in FCC by approximately 1 order of magnitude. A wide range of diffusion coefficients is exhibited by BCC metals. This is correct. For both FCC and BCC metals, lightest element in a group of periodic table exhibits the lowest diffusivity when compared on the homologous temperature scale. Option D is this is correct because this has been an empirical relation that is observed for several group of periodic table elements, and therefore, option D, both FCC and BCC metals, lightest element in a group of periodic table exhibits highest self diffusivity. This is not correct. It is the C option, the lowest diffusivity is exhibited by lightest element. So, the correct options are B and C. Question number 15. Hydrogen isotopes have low atomic weight and hence are not suitable to study the isotope effect. True or false? This is false. In fact, because the ratio of the atomic masses are fairly large, in fact, hydrogen isotopes, the isotope effect has been studied well in these hydrogen isotopes. So, if you remember, we had put some tables also showing the diffusivity of hydrogen, deuterium and tritium in several metals, and you can see for example, the delta H is different for the different isotopes. For deuterium and tritium, it is same in niobium, but for hydrogen it is much lesser. And similarly, if you see in vanadium also, hydrogen and deuterium shows a different activation enthalpy. Question number 16. For carbon diffusion in BCC iron, the value of correlation factor is this, and the value of correlation factor will become dash when the carbon diffusion is studied in FCC iron. So, here you see that the carbon diffusion in BCC iron, so carbon occupies the interstitial position, and we know that the diffusion in that case happens by the interstitial mechanism, and therefore, the value of correlation factor for a species diffusing through interstitial mechanism is equal to 1. And the reason is because there is no, the interstitial sites are available everywhere, and therefore, the atom can always find an interstitial site to make a exchange. And the value of correlation factor will become when carbon diffusion is studied in FCC iron. Even if it is an FCC iron, carbon still occupies an interstitial position only. So, please remember that in that case also the value of correlation factor is 1. So, the last question of the tutorial, which of the following phase transitions are accompanied by decrease in diffusivity? So, this we saw that by an increase in diffusivity. Which of the following phase transitions are accompanied by increase in diffusivity? So, alpha iron to gamma iron, that is a BCC changing to FCC. So, BCC changing to FCC is usually causes a decrease in diffusivity because you are moving to a close pack structure. Whereas, in the option C and D, you have alpha titanium to beta titanium or alpha hafnium to beta hafnium, where the HCP structure is changing to BCC structure, and in that case the diffusivity is seen to increase. Similarly, paramagnetic to ferromagnetic transition also leads to an increase in the diffusivity values. So, the correct options in this case are B, C and D. So, with this we will end today's tutorial lecture, and we will continue with last 2 weeks of lectures in the next week onwards. Thank you.